Good morning and welcome to this new Hispalyt webinar in which we are going to talk about the European Life Superhero project focused on the energy efficiency of ceramic roofs. As indicated in the program, this webinar will be held in English. But first, I would like to comment some technical specifications about the webinar. The workshop will be streamed live on Zoom webinar platform. And although most of you have already used it, I would like to point out that you have a chat button to send us any question you may have. Those attending the workshop do not have the microphone option activated. But if you want to intervene during the final debate, you have two options. Write your question in the chat or click on the raise hand icon, and we will activate the microphone. You can leave your questions and comments in the chat during the webinar. At the end of the webinar, during the debate, we will go over the message you have written. The speakers will answer your questions. This event is also being streamed live on YouTube Live, where the webinar is being recorded and could play immediately on the Hispalyt YouTube channel. Getting back to the issue at hand, it is important to highlight the maximum sustainability and efficiency of ceramic tile roofs. Extreme climate events have considerably increased in recent years. This clearly indicates that climate change is already a reality and its impacts will most probably challenge the quality of life in our cities. At the same time, European cities are projected to grow from housing nearly 73% of the population now to more than 80% by 2050. Urban heat island, the phenomenon resulting in the increase of temperature is in dense areas of cities in comparison with rural areas in the exacerbated too. The combination of these two important phenomena will result in the coming decades in ever higher temperatures inside buildings, especially in existing ones with poor energy levels. Consequently, comfort and health problems will especially occur for weak and disadvantaged groups, elderly and sick. Life Superhero project proposes an effective, sustainable, and low-cost answer to cities and buildings overheating using building passive cooling technologies, which allow to reduce the temperatures of building envelope, roofs, and walls, and consequently of the surrounding air, thus limiting urban heat island, rather than increase energy demands from artificial cooling. Among building passive cooling solutions, the use of ventilated and permeable roofs is the most sustainable and promising strategy. Life Superhero promotes innovative building passive cooling concept and aims to diffuse the use of ventilated and permeable roofs and heritable-based roofs in existing and new buildings. To learn more about this project in which Hispalyt participates, today we have three speakers who will give us all the details. To start our workshop, we have two presents of Giuliana Bonvicini, Materials Engineering at the University of Bolonia, degree in Chemistry at the University of Bolonia. Nowadays, she covers the position of Environmental Department Head of Cubiertas Cerámicas. She's also part of the working group about safety or workplace in ceramic industry. And she has been designated as supporting expert of the Ministry for the Environment and Protection of Land and Sea. Giuliana took part in several national and international projects. In particular, she's the coordinator in Life Superhero. Giuliana is also author of about 40 scientific works about publication in international journals with impact factor and about 30 conference presentation, also as invited speaker. I'm opening the floor to Giuliana. Giuliana, the word is yours.
Thank you very much for your presentation. I will share my screen. I hope everything will work fine. Can you see it?
Yes, it's perfect.
Perfect. So my duty today is just to break the ice. I'm the first speaker today. I'm the coordinator of the project, and I will just give you an overview of our goals and what we are going to do in the next years. And we focus specifically on the action C1, that is the development of a standard test method for air permeability. The problem that we have to face, that we want to face in our project, has been quite good, quite well introduced by the first speaker, by Elena, because as you know, we have to face a climate change in these few years. And we had to face summer heat waves in many times. And of course, this means that the urban heat island effect on in the city and the surrounding area is quite exacerbating. And this, of course, creates a building overheating while people are living. And the people to in some way reach a maximum comfort living in the city use a air conditioning, and that means higher emission of gas and also a high energy demand. And this creates also, again, a summer heat waves in the city. So this is a vicious cycle that we, in some way, want to stop, interrupt. The strategies to do so could be divided in two different goals: the adaptation strategy and mitigation strategy, with different solutions. If we can go through a legislation at European level and also around member state regulation, we can see that the actual European policy and also green building rating system, and again, the public procurement actually address the urban heat island effect, mainly suggesting the use of green and cool roof. From the other point, the same problem is faced, for example, focusing on winter heating saving through the envelope. And you can see, for example, in the picture in the slide, that how thicker it became the envelope of the building during the years. But we know, also because we have a scientific public, and we have and we are really aware about the result, that this solution is not quite effective strategy, in particular in hot climates, to limit the building cooling needs, to improve the indoor comfort. What is the impact of roofing technology on urban heat island effect? I can present this slide because it's just in some way a summary of current solutions that we have, for example, in our regulation framework in Italy. If you can just go through, we have different code, for example, Italian building code, Italian building green public procurement, a building green rating system that's called Itaca, and also we have building green rating system that's called Hispalyt. If we can see the solution that are proposed in this regulation, we just see, for example, the roof solar reflectance, green roof, as I've already said, and just one in the Italian building code, we have a passive cooling technologies on passive cooling ventilation. So if we can speak about green roof, if we want to speak about flat roof with tiles, you can see here there's no way to push our technology and our product, because we want to push the use of roof tile made by clay. What we propose with this project? We propose a solution that is using the ventilated and permeable roof, has a sustainable and a strategy to reduce building overheating. We can combine with our solution the ventilation system due to the dissipation of the heat from the sheeting and roofing material. And at the same time, we can couple it with the high permeability of the roof tiles, because we have a discontinuous covering of the roof. And in this way, it's possible to obtain an increasing of the cooling performance of the roof and for this reason also for the building. The background is coming from another European project that is called Life Eurotile. This project that is already finished and make some tests with and develop a roof tiles with a particular specific shape made by clay. So there's no additive, no new material or specific, for example, non-natural additives in the mix. And this kind of roof based on Eurotiles can reduce until the 50% of cooling energy compared to other solutions. But what it happened? We find a solution, but we do not have any, let's say, possibility to push this solution because right now the regulation, as I said before, doesn't recognize the cooling potential of ventilated permeable roof. So, for example, the general public, the professional, the building stakeholders are not aware of the benefit of these new technologies. For this reason, we presented and make a new proposal for the Superhero project. I present here the consortium. The consortium is made by Confindustria Ceramica and Hispalyt, that is a perfect host for us today. They are the Association of Tile and Brick Producer, Italian and Spanish association. We have in the consortium Industria Costo Possagno, Terreal, and Giuliana, that they cover more or less the 50% of the European production of roof tiles made by clay. And then we have Centro Cerámico, that's me, and the other speaker representing CTMC and also University delle Marche, that we are 3 research centers in Italy and in France that we are able to test the performance of the tiles roof. The project is quite long, it's 5 years. Is under the LIFE program, and the specific topic of this program is the climate change adaptation. So we have started the project in summer of 2020, and we hope to finish in time in June of 2025. Which are the objectives and the scope? Life Superhero is a best practice project. We want to promote the use of this ventilated permeable roof, because we strongly believe that it could be the perfect system for passive cooling of the building, increasing building occupants and city summer comfort, and this means an adaptation strategy. And also, we think that it's possible to decrease the building's energy and greenhouse emission to offer a mitigation strategy for the situation that we have to face right now. To do so, we exploit the activity in 4 main pillars that are illustrated here. The first action that we call action C1 is a standards and regulation proposal. We want to overcome the lack that we face in the regulation to diffuse the ventilated permeable roof. And we want to act in different levels. Diffusion, for example, on also on regulation of European level at the member state level, and also on technical scale. So we want to product from product to building level, implementing a standardized air permeability method, propose a updating on green rating system, and also improving existing CAN standard for building energy calculation. The other main action is represented by C2, that is the best practice for realization of Eurotile-based roof. And with this activity, we want to develop guidelines to renovate building using innovative solution for the roof. On this action, the speaker after me will focus specifically on the details, the technical details. Then we have action C3, and it's regarding the development of Superhero software. Because of course, if we want to push this solution on the market and also in the regulation, we need to have a support tool for building consultant and professionist. In this way, they can calculate different performance of different solutions applied in a specific building, and they could have a supporting tools for administration and consultant to make the proper decision. Then we have the action C4. C4 is on replicability, transferability, and best practice creation for type producer, because, of course, we have 3 producers inside the consortium. We want to demonstrate that produce a roof tiles for a passive cooling solution with clay is quite easy. So even if they don't produce right now permeable roof tiles, they can change something with no extra cost in the production cycle and to be prepared to put on the market this kind of product. So we want to amplify, of course, all the benefit that we can reach thanks to the project. I will focus right now on the C1 approach specifically because my presentation will focus on this action. As I said, regulation in force on building energy efficiency are mainly focused on winter saving, neglecting effective solution for summer cooling. What we have identified in the regulatory to address this project is the lack of standard. We have no standard defining properly the air permeability of roof tiles. We also found a lack of a knowledge of ventilated permeable roof environmental performances in the building rating system and building green public procurement. And also we think that something is missing in the standard method to assess the VPR cooling performance. So we need a method to be able to make some calculation and decide which is the best solution to install in a building. I will focus my presentation on the action C1.1 that is specifically on the air permeability test method, but the action C1 is mainly organized in 4 subtasks. One is the method that we will see after. The other is the proposal of specific credit for building environmental rating system and green public procurement, including the VPR benefit that we want to show and demonstrate with this project. We create a product certification based on a self-declared environmental claim, the label of type 2. And also we will propose an improving of the existing standard to take into account the ventilation and the permeability of roof into the energy building calculation. Focusing on the action C1.1, I repeat myself, is the air permeability test. We need to implement this test because to have a product to put in the market, we need an European technical assessment. It's called esta, named Air Permeability Roof. To produce this document, we need to develop a method of testing that has to be in some way taken into account from a recognized technical assessment body for the assessment of VPR performances. In this way, we can voluntarily make the CE mark on this construction system, and we will be ready for the market. I don't know if you are aware about the esta procedure, so I just a slide summarizing some point. What is the esta that I've already said, and the European assessment document on which the esta would be based. That contain a general description of the construction product under investigation, the list of the essential characteristics that according to us are relevant, and the important thing is the method and the criteria for assessment the performance of the product. And also we need to list the principle for the implementation of the system for assessment and verification of the constancy of the performances. This procedure could be simple, just saying like that, but it could take 5 months if INEAD is already present. And we think that we need a couple of years to develop. And so we hope to finish all the work during the project. To do so, how to proceed? In the proposal, we arrange a round-robin test in 4 laboratories: Centro Cerámico, Università delle Marche, CTMC, that are in the consortium of the project. And also we involve BMI, is external laboratory, that makes some tests in the previous project. We organize this round-robin test to collecting data and figures for the definition of the standard ETA and the CEN. The samples that we want to test is around 18 type of roof tiles, just to cover almost all different typology of roof tiles on the market, available on the market right now, and will be supplied from the 3 industrial partners, Edilians, ICP, and Terreal. In these 18 roof tiles that are standard, we also have 2 Euro tiles roof tiles. That means the roof tiles that we have developed in the previous project, that we, thanks to which we have also demonstrating the benefit of VPR made with this Euro tiles roof tile. For the test method, the first thing for us was to have some references on the existing standard. So we found a British standard and STM that are listed here. But the goal of this method is to assess the roof resistance to wind. It's not exactly the property that we want to measure. Then we also have another ASTM and an ISO. But the goal of these 2 methods is to assess the building envelope airtightness. So we decided to take into account the British standard BS 5534 and specifically the Annex L. We use this standard in some way to replicate the equipment that we have and that we produce and that we have in the 3 laboratories. So we have 3 twins equipment in our laboratories. That it, as you can see, the scheme is quite simple. We have an airflow generator, an airflow meter, and pressure difference measure device. Of course, we need also system to weigh the samples, to measure the ambient temperature and local air where we will perform the test. And we also pressure different measuring device because we want to test a different range of pressure. And specifically also, the equipment is made by a box. It's called plenum chamber that is made by wood. I have some pictures in the slide, in the next slide, on the top of which we will put an installation of our roof tiles. So we have a portion of the roof tile made by our clay. The installation, where you can see in the picture here. So this is a roof tiles. And these are a kind of installation. And you will see we have all the tiles, roof tiles sealed. And according to the standard, we decide to follow the standard also for this, this issue, to leave free just 4 of the roof tiles put in the installation. The experiment consists of blowing and also sucking air down to the pipe into the plenum chamber. And we will record the difference in air pressure between the inside and outside the box. And also we will measure the volume of airflow rate inside the pipe. In this way, we can in some way determine the pressure drop coefficient that is used also to calculate the permeability factor. Because we want to measure, I remember you, the possibility of this discontinuous layer to dissipate heat from the roof, from the building, to outside. Here you will see some of our equipment This is the one in CTMC. This is the one, for example, in Centro Cerámico. This is the one used in BMI with an installation of roof tiles on the top. You can see here, for example, we could also test the installation changing the inclination of the box. We don't know if this will affect the test because in the standards there's no reference to the angle of inclination, but we want also to test this kind of parameters. These are the list of typology of roof tiles. So we have 3 industrial partners that will supply different kind of roof tiles. So we hope to have covered all the most part of the product available in the market, and all these roof tiles are made by clay. Of course, we have to perform the test, and we have some formula here just to let you know, because we have to calculate what we need, the air permeability, that is like this. Of course, all the parameters are a geometrical parameter, for example, the pattern, the gauge, the kilogram, and the weight of roof tiles, the test rig area of the roofing element assembly, and we have also the volume flow rate, the pressure, and the length of path in which this installation is creating. So we perform the test, we have to measure, calculate, and also we have to compare the result in 4 laboratories from statistical point of view in order to calculate the air permeability and define the performances of the specific roof tiles installed on the instrument. All this to do what? We strongly believe that among a passive cooling solution, the use of ventilated and permeable roof is a sustainable strategy. So we can use it to perform and to, in some way, increase the energy rate of the building. We can reduce the external roof covered temperature. In this way, we can mitigate the heat in the surrounding area, mitigating the urban heat island effect. And also, we can use this installation to reduce the internal temperature and incoming influxes. That means that the people won't be forced to use higher energy for cooling the building, and in this way also decreasing the emission of heat and pollutant and gases in the environment and surrounding area. And we have also demonstrated this in live hero tile. We can do this with a low cost because, as I said, the transformation of the production cycle is not so expensive, and also the new installation of the roof with the roof tiles is not expensive. It's not, there's no higher cost, no additive cost. We know that our product, roof tile made by clay, are durable and sustainable materials. So we can also use this product in a circular economy, as we are doing right now. And we also combine this solution with, for example, other solutions. So it's not the unique and only solution. So I hope that our study will bring, push the clay roof tile on the market and will help to face this situation of climate change right now. Thank you very much. If I understand, I will give the floor to next speaker. So I stop to share. Okay, perfect. It's already done.
Okay, Giuliana, thank you very much for giving us an overview of the project showing the benefits of the ventilated permeable roof based on hero tiles. It is really interesting, the implementation of a standardized air permeability test method, which will be used to update the green rating systems of building and public procurement by including ventilated and permeable roofs in the energy calculation of buildings. Next up, we have Elisa Di Giuseppe, is Associate Professor of Architectural Building Engineering at the Department of Construction, Civil Engineering and Architecture at the Università Politecnica of Marche, Italy, where she currently teaches technological retrofitting of existing buildings and sustainability in building construction. Elisa is co-author of more than 130 international and national scientific products and has been an invited speaker or presented or enriched at various events, such as conference, international and national fairs, industry and university workshops. She has participated in more than 15 funded research projects or industrial research agreements. She is a member of the editorial board of the Journal of Building Physics, the Journal of Frontiers in Built Environment, and the Italian journal Costruire in Laterizio. I'm opening the floor to Elisa. Elisa, the word is yours.
Thank you very much. So I'll share my screen. And start the presentation. I hope you can properly see it. Can you?
Yes, it's perfect.
Okay, thank you very much. So the previous presentation provided by Giuliana presented the general overview of the Life Superhero project. Now with my presentation, I will focus on some specific activities which are currently ongoing on the project's buildings pilots. So these activities are part of the second main pillar action of the project, whose aim is to develop a best practice for the proper design and installation of the hero tile-based roof. So for the HBR in both new and existing buildings. And this will be a solution for climate adaptation and mitigation. The action will be realized on 2 existing buildings, which are actually covered by a flat roof. And over this flat existing roof, a new attic floor will be realized, of course, covered by hero tiles. And monitoring activities will be carried out in these buildings before and after the implementation of the HBR in order to collect useful data on the thermal performance of the roofs, on the indoor environmental quality, and on the occupants' behavior. Action C2 is actually composed by 3 sub-actions, which are the following. The first one is about the thermal, energy, and behavioral monitoring activity in the buildings. The second one focuses on the HBR project and installation. And finally, the number 3 provides the creation of a data sharing platform to collect and share monitoring data with non-expert users, but also with stakeholders and interested people. So the main contents of my presentation are the following. I will present a description of the Life Superhero building pilots and of the renovation plan they are involved in. Then I'll present more details on the monitoring activity on the pilots and the way of data sharing. Then I'll present the preliminary monitoring results on the buildings obtained during last summer. And finally, I will present another activity which concerns the measurement of the radiative properties or the optical properties of the building materials and especially of the hero tiles. So going into some details of the buildings, they are 2 existing multi-story residential buildings located in Reggio Emilia, which is here in Italy. So with a climate in the range of Mediterranean and humid continental, which is, however, characterized by quite hot summer, so by special thermal stressors in summer. These buildings have been built in the 80s and have a flat roof, as you can see. So they represent a good context to support the creation of the best practice to shift the flat roof into lightweight attic floor with HBR. Each building will be covered by a different hero tile typology. Portuguese tiles supplied by our partner ICP in one case, and Marseillaise tiles supplied by the partner Terreal in the other building. The first building has 5 flats in the last level, with a covering surface of about 240 square meters, while the second building has a flat roof in both the second and the third levels, covering again 5 apartments for a roof surface of about 350 square meters. We are going to totally monitor 24 rooms in the buildings, which are actually occupied by 11 people. Unfortunately, some flats are empty at the moment. However, we are also monitoring their thermal condition and energy performance in order to set a proper baseline for the assessment of this performance, even in unoccupied conditions. The future HBR installation is part of a broader renovation plan which involves the buildings. And this plan will be carried out in 2 steps. During the next autumn, the buildings will be retrofitted with an external insulation layer, and by also replacing the existing windows. And then during autumn 23, the new attic floor with the HBR will be realized. So consequently, we will monitor the energy and thermal performance and occupants' behavior in 3 different conditions: the existing state, during 2 summer periods, as we already started last June 21, and we will continue, of course, during this summer. Then the buildings with the renovation of the only vertical envelope, and finally with the addition of the HBR. As said, a complex monitoring system was implemented in the buildings last year to detect the indoor and outdoor environmental condition, the occupants' behavior, and the roof thermal performance. It consists of low-impact wireless devices connected with the LoRaWAN communication system in order to get a lower impact on users' daily life, and also to allow an easier transmission and data storage. So data are collected from different sources and then aggregated within a database. A weather station was installed at the height of about 1.5 meters on the roof of building 2 in order to monitor the local outdoor climate condition, and as the air humidity and temperature, global solar radiation, wind velocity and direction, and the rain. In the flats, some sensors, as these you can see in the picture, were mounted on the wall for measuring the indoor environment in the living rooms and in the bedrooms, which are the rooms air conditioned in the buildings. In particular, these sensors detect air humidity and temperature, human presence, illuminance, and CO2 emissions. Buildings occupants' actions are also monitored to evaluate the way people interact with building systems to improve their comfort conditions. In particular, we are detecting the windows opening and closing activities with these contact sensors, and also the air conditioning used through some energy counters. We are also regularly performing interviews and surveys with the building's occupants to assess their overall thermal sensation and comfort. And finally, we installed some specific sensors to monitor the actual roof thermal performance. So these are sensors to measure, for instance, the surface outdoor temperature, this one, and also the air temperature near the roof surface with this probe, the indoor surface temperature, and also the incoming heat flux through the roof with this sensor. Of course, during the next monitoring period, especially when the HBR will be installed in the last project year, the number of probes to detect the roof thermal performance will increase in order to measure the thermal properties in the different interfaces of the HBR, and especially in the ventilation channel. And here you can find an example of a floor plan with the implemented monitoring system. So you can see the complexity and the number of sensors that have been installed to detect a complete overview of the building and occupants' behavior and performance. Within this action C2 of the project, we are also developing an interactive web-based platform to share monitor data to different stakeholders. It is named Human Behaviors Monitoring Data Sharing, so HUBES. HUBES will show qualitative and user-friendly data to unspecialized users, for instance, the building's occupants themselves, while it will show quantitative data to specialized stakeholders and policymakers, and also to researchers and to all people interested to the project. This platform indeed will be part of the project website and also diffused through the Covenant of Measure and through the Climate Adapt platforms. You maybe know these platforms. The first one, Covenant of Measures, is a movement of thousands of local governments for local climate and energy actions, while the Climate Adapt is a partnership between the European Commission and the European Environment Agency on climate topics. And its goal is helping users to access and share data and information. So up to now, we are building the architecture of the platform. We managed to insert the separated data from each sensor, and then we are going to aggregate them in selected KPI, that is key performance indicators. Concerning the inhabitants of the buildings, a web application will allow them to download data and also to receive a feedback on their energy behavior and on the apartment performance. The platform will consist of the user profile. The access to only certain information can be allowed. Then a visualization of the plan of the apartment with the location of the installed sensors, a display of the quantities monitored by each sensors and of aggregated KPI, And finally, information on the status of the sensors. We are also planning to include a message notification system to improve the use of information and also to provide feedback to the users. So in this way, the information can be sent directly to the user's devices without necessarily having access to the platform. Let's now briefly see the first preliminary monitoring results collected last summer for an empty apartment and an occupied apartment in Building 1. We selected a period of 3 extremely hot days with peaks temperatures about 36, 38 degrees. And we noticed that the actual roof outdoor surface temperature, here in the light blue line, reached very high values in both cases, with peaks between 60 and even 70 degrees, depending on the roof orientation. The occupied flat presents higher values of the heat flux through the roof, here in yellow line, and an irregular oscillation, which is obviously due to the activation of the air conditioning. Concerning the indoor environment, in these graphs, you find the indoor temperature with the red line, together with the external temperature in the black line. And the empty flat without air conditioning is characterized by a very high indoor temperature, even over 30 degrees, while the occupied flat has a lower indoor temperature between 23 and 28 degrees, depending on the use of the conditioning system. And this is also highlighted by the regular trend of the line. And these are the same results obtained for different apartments of building number 2, but the general trend is similar, with observed outdoor roof temperature reaching until 75 degrees. And concerning the indoor temperature, here we also have values reaching 30 degrees in the empty flat. Questionnaire provided to the occupants of the buildings then confirmed a general thermal discomfort sensation in the indoor environment. All the occupants consider their thermal environment between warm or hot. 80% of them consider it unpleasant in terms of thermal comfort before the installation of the air conditioning, while all of them consider it just acceptable when the cooling system is installed and used. From the results I presented, maybe you could notice that the recorded heat flux through the existing roof are actually quite low. Indeed, when even if the buildings were both realized in the 80s, they present an insulated roof, which is not a common practice in Italy for that period. We did not know this before starting the project, but we recently realized an inspection on the roof and also discovered that a further intervention has been carried out some decades ago, maybe to improve the waterproofness or the sound insulation of the roof. So in consequence of that, the existing roof have a better performance than that assumed initially. And this risk making the baseline performance of these buildings not really representative for the typical Italian 60s, 70s, 80s buildings. And this means maybe reducing the impact of installing the HBR in the next years. So in order to mitigate this risk, we decided to perform two further actions. Firstly, in some areas of the roofs, we removed the additional layers, and this summer we will carry out new thermal measurements. And the second one is that we are realizing reliable energy models of the buildings that we can then use to perform parametric analysis, parametric simulations of the performance of the buildings, eventually defining new baselines. This means that we will calibrate these energy models against the real collected data, and then we will perform the simulations also in a condition of the roof without insulation, to define a better baseline and the better comparison of the performance before and after the installation of the HBR. And finally, here I'll present a further activity we are carrying out, which is not really part of action C2, is part of another action of the project, but it's useful for the calibration of the energy models I just talked to you about. And especially, I think you can find it interesting. As we are performing measurements of the optical properties of the materials of the external envelope of the buildings, also including the materials that will be installed, that is the hero tiles. So actually we started this activity especially from this. So the hero tiles produced by our partners Terreal and DCP. And then in the next month, we will perform further measurements on the material samples removed by the existing roofs of the demo buildings. We measured the thermal emittance of these samples and also their solar reflectance, and then calculated the total solar reflectance, and from this and from the thermal emittance also the solar reflectance index, SRI. These are the reflectance spectra we obtain for the different samples. And here you can find the summary of the results obtained in terms of emissivity, solar reflectance, and the solar reflectance index. Out of curiosity, I will show you a comparison of these results and the values included in current Italian mandatory or voluntary regulations that Giuliana already showed you. So the obtained reflectance is higher than the threshold imposed by the actual regulation on the building's energy performance in Italy. The SRI is higher than the threshold provided by the Italian Green Public Procurement, and also of the value provided by the buildings rating system LEED that you maybe know. So this result is interesting as it demonstrates a good radiative performance of the hero tiles that can also enhance the global passive cooling performance of the HBR that Giuliana just presented you. So that's all concerning project action C2. but of course, I'm available if you have some curiosities or questions at the end of the webinar. Thank you very much.
Thank you very much for your presentation, Elisa, and thank you for explaining to us the renovation project to be carried out on 2 existing multi-story residential buildings in Reggio Emilia, Italy, currently covered with a flat roof, where the vertical envelope will be insulated, and finally a horizontal base roof with Portuguese and Marseillais styles will be installed. An interesting project during which the thermal performance of the roofs, the indoor environmental quality, and the occupants' behavior will be monitored by a sophisticated low-impact wireless monitoring system. Finally, we welcome Gianluca Martini, who is a research technologist and PhD in architectural engineering at the Department of Construction, Civil Engineering and Architecture of the Polytechnic University of Marche, Italy, where he has been a lecturer in university courses. Gianluca has carried out more than 40 research papers and has participated as a speaker in several international and national scientific conferences. Gianluca also has participated in different European projects funded under the Horizonte 2020 and LIFE actions, and in other projects funded at national or international level. Gianluca, I give you the floor.
Okay, let me share my screen. Good morning, everybody. Okay, you can see, I think, yes.
Yes.
Yes, okay. Good morning, everybody. In this presentation, I will briefly show you the basic principles that we have followed in the Life Superhero project to model the interaction of ventilated permeable roofing solution with the urban environment in order to estimate its impact and benefits at the urban scale. In particular, we developed a specific software tool starting from an existing one that can be used by building engineers and stakeholders to compare the impact at the district and urban scale of different roofing solutions, also considering different climate contexts and different building typologies. These activities are preliminary and are part of the Action D1 of the Life Superhero project. Today we are we will also show the first numerical results carried out to compare the impact and benefits at the urban scale of BPR and other roofing solutions. More in detail, the main scope of this action called environmental impact assessment and monitoring concerns the quantification and monitoring of the environmental benefits obtained by VPR and HBR solutions, also with respect to other existing roofing solutions such as green roofs, cool roofs, and metal roofs. The action is subdivided into 2 main sub-actions, which are the assessment of the impact of VPR on the urban environment carried out through both numerical and experimental activities, and the assessment of the environmental impacts over the life cycle of VPR. Today, we will just focus on the progress on the progresses of sub-action D1.1, which is the only activity currently started in this action. Sub-action D1.1 in particular consists of numerical and experimental activities. Numerical activities regard simulation that will be performed through a software for urban climate to assess the influence of alternative roofing solutions, such as HBR, cool roof, green roof, flat roof with waterproof membranes, metallic roof on urban areas. Experimental activities are instead finalized at the collection of thermal data on demo buildings in Reggio Emilia, used to demonstrate the HBR benefits in terms of surface temperature reduction and to calculate the HBR equivalent reflectance values to be used in the simulations. The expected results of this sub-action regard the implementation of VPR in urban climate models, the assessment of the impact of VPR on urban heat island, also compared to other roof types, the demonstration of the HBR benefits in terms of temperature reduction in the roof's internal and external surfaces, which is a KPI of the project, and the equivalent reflectance values for the hero tiles. As I already said, this presentation is mainly focused on explaining the approach used in the numerical simulation and then showing the first numerical results. But why we are talking about the impact of VPR of the ventilated permeable roofing solution on the urban heat island? Because of some of the results obtained in the previous life hero tile project, as already Giuliana summarized in the first presentation, which allowed demonstrating that VPR can be used to reduce the cooling energy consumption due to air conditioning, and then it permits reducing the heat released by air conditioning equipment in the urban canyons, in the urban environments. And VPR also allows reducing the temperature of the tiles, which dynamically interacts with the urban environment by exchanging heat through convection. Also, why we need a comparison with other roofing solutions in our numerical simulations. As already said by Giuliana, due to the regulatory frameworks on urban and building overheating in several countries, in Italy, for example, the actual building code sets limits just for the, but just for the solar reflectance of coverings, while the use of passive cooling technologies such as VPR is just mentioned, and no calculation methods are provided. The green public procurement and the building green rating systems explicitly ask for the use of green or cool roofs. These roofing solutions claim to reach important environmental results in terms of benefits on the urban heat island effect. Hence, they considerably spread during the last decades and are included in the actual codes. However, as already said, we noticed the absence of VPR in codes, and this absence lies in the fact that there is no robust literature on the possible benefits of ventilated roof on outdoor ambient temperature. It should be also said that cool or green roofs are not always the best solution when considering factors such as the local climate, aesthetics, or meeting local architectural and landscape constraints. Moreover, the reflectance of cool materials and then their effectiveness is reduced over time due to aging, atmospheric deterioration, and dust. So these solutions need cleaning and maintenance, which are also quite high for green roofs too. Conversely, we know that VPR is a low-cost, low-maintenance, durable solution suitable to be applied in European city centers, and it entails a cooling energy reduction. So the idea of this sub-action is to assess its environmental benefit on the urban climate, considering the heat balance at the roof level, and the air conditioning heat release in the urban canyons. Before continuing with this presentation, it is important to define what is intended with urban heat island phenomenon. Indeed, we must consider that the urban heat island is a complex phenomenon that involves urban surfaces and different air layer that have in common in the urban area to be on average warmer than those observed in rural environments. More in detail, we can distinguish different types of urban heat island, such as the surface urban heat island, the canopy layer urban heat island, and the boundary layer urban heat island. The surface urban heat island refers to the urban surface temperatures, which are generally higher than rural one, due to the specific properties of the artificial materials that are used in the urban areas. The canopy layer urban heat island refers to the air temperatures of the urban canyons, or more simpler, the air temperature between buildings. The main drivers of canopy layer urban heat island are the heat storage and release due to the thermal properties of the building materials, the anthropogenic heat released from building, but also from traffic, the short and long wave exchange in the urban canyon, the heat fluxes due to the evaporation caused by the presence of vegetation and water bodies, and the wind speed that can be present in the urban canyon and can be different from the rural one. Boundary layer urban heat island intensity extends from above the urban canopy layer and is the result of anthropogenic heat from roofs, the heat gains from warmer canopy layer, the heat gains from overlying stable air by convection exchange, the shortwave radiative flux convergence within polluted air, and the thermal re-emission. The VPR can have an effect on both the urban canopy layer due to the heat released by the air conditioning equipment and the urban boundary layer due to its heat exchange with the surrounding air. The impact of VPR can occur mainly on the temperature of the boundary layer due to the thermal exchanges with the surrounding air, but also on urban canyons due to the heat generated by air conditioning machines. To assess the roof interactions with the city's climate, model simulation are needed. Today, we have different urban climate models that can be used depending on the target scale of investigation. These urban climate models have different characteristics, depend on the different scales, but also they differ in the treatment of the land surface and the resolution at which balance equations are written. Trying to summarize, at the mesoscale or city scale, there are models able to analyze a whole city and its surroundings for several kilometers. However, in these cases, the resolution is very low. The horizontal resolution is very low, with cells, grid cells with dimensions of more than 200 meters. This scale of resolution does not allow for an explicit representation of the urban areas. Moreover, these models require accurate and specialized climatic input data and entails high computational costs. At the local or neighborhood scale, district models extract urban areas ranging from 100 meters to a few kilometers. Building shapes, materials, and surface properties can be explicitly considered in these models, which means that each building can be modeled separately, or that average values can be taken into account to characterize an homogeneous area in the urban scenario. In this case, we can distinguish two families of models. The first one include computational fluid dynamic models, CFD, that use the geometrical representation of the district and mesh it, so they explicitly solve the governing equation for the interchanges. The main drawback of these models are that they entail high computational costs, and then the results are limited to short periods. The second family includes parametric models that do not represent explicitly the urban shapes, but use, as already said, average parameters that translate their impact. As a result, this model produces averaged microclimatic results for the examined district. However, they entail low computational costs. Then they can be used to obtain results for long periods. For instance, the heat waves can be analyzed for this, in this way. Through these models, it is also possible to estimate the interaction between building energy consumption at the neighborhood state and the urban environment. Finally, we have the micro or street scale model that are able to analyze the physical processes in a urban area of a few meters. As example, focusing the analysis in the canopy, in a single canyon, in a single urban canyon. This list of urban climate models is not meant to be exhaustive, but wants to simplify a quite complex framework. Indeed, different models can be combined with each other to obtain results at different scales. Despite this, it can be said that none of the existing microclimatic models currently allows considering the thermal behavior of a ventilated permeable roof and its interaction with the urban climate. Given this picture for the action D1.1, we decided to use the software called the Urban Weather Generator, which is a parametric district model, which is already validated in literature and allow us to calculate the urban air temperature within the urban canopy layer and the urban boundary layer, starting from the rural weather conditions. also using as an input various properties of the target urban district, such as the building streets, the vegetation, the material properties, anthropogenic heat, etc. The reason behind the choice of this tool is that it is open source, hence we can directly modify the original code that is written in Python to model the heat balance of the VPR and its interaction with the urban environment. Moreover, it considers the features of the urban canyon in terms of geometry, surfaces, and material properties. It also provides us a good balance between accuracy and calculation speed that allow us to provide results for year of simulation. And then in literature, there are several examples of its application and validation. In the software, as can be seen from the figure on the right, the urban canopy layer is the atmospheric layer that goes from the ground to the average height of buildings, being then representative of the this layer representative of the air temperature at the street level, while the boundary layer is basically the air above the canopy layer. In this action, we will mainly refer to the urban canopy and boundary layers. How does UWG works? The UWG calculates the urban air temperature through 4 coupled physical models based on the rural meteorological data and the city mesoscale information. These models represent the energy balance equations between the air masses above the rural area, above the urban area, and in the urban canyon with the urban elements. The UWG output are the urban microclimate condition in the canopy and the boundary layer. As a result of the rural weather condition and the various properties in the target neighborhood. UWG also solves the building indoor heat balance and calculates the anthropogenic heat portion released by the buildings and the air conditioning equipment in the urban canyon. In this sense, it can be used to quantify the reduced environmental impact on the urban Italian provided by the HBR compared to our reference case. In this figure, the resistance capacitance model adopted in the UWG to model interaction between the building energy model and the urban canopy layer is shown, where each resistance corresponds to a heat exchange due to conduction and convection and radiation between elements and spaces. While arrows are referred to the different indoor and outdoor heat gains due to the, for example, people, electric equipment, HVAC heat waste, and traffic. However, as we know, in a ventilated roof, the heat exchange is more complicated than a typical roof. Indeed, in a ventilated roof, as in VPR, we have additional and complex convective and radiative heat transfer mechanisms in the air cavity. In particular, with respect to traditional not ventilated roofs, the ventilation in the air cavity of the VPR passively contributes to reducing the tile surface temperatures, which contributes in turn in reducing both the related heat released in the outdoor air per convection. However, the ventilation in the air cavity also releases warm air in the outdoor environment. As a result, the amount of heat transferred per convection from the roof to the outdoor environment remains quite unchanged, even if subdivided in first part coming from the external roof surfaces and another part coming from the air cavity. Cooler tile, however, also allows to reduce the heat flux entering into the indoor environment. As a result, in a building with VPR, a lower heat waste to the outdoor environment and energy consumption of the air conditioning system is produced due to the passive cooling action of the VPR itself. To model the VPR thermal behavior in UWG, we modified the actual heat balance equation at the roof level to get the same heat flux entering the building and the same heat released to the external air occurring in a real VPR. In particular, in the heat balance equation of the original UWG software, we consider the amount of heat exchanging through ventilation in order to have the same heat flux entering the building and the same surface temperatures. The amount of heat removed through ventilation has been estimated in this preliminary phase through the calibration of a building energy model, representative of an experimental mock-up with VPR located in Ferrara and monitored in terms of heat fluxes, surface, and air temperatures during the previous Eurotile project. In particular, we have seen that the heat removed through ventilation inside the VPR air cavity varies its intensity during the day, and it can be considered as proportional to the solar radiation that hit the tiles during the day. So we consider this proportionality to estimate the orange arrow in the figure during the different hours of the day within the UWG software. The total heat transferred per convection from the roof generally contributes to the heat balance occurring in the boundary layer. However, in some conditions, due to the high speed, for example, high wind speed, or for the particular dimension of urban canyons, in particular where they are particularly large, it is possible to observe a more marked contribution of this heat, this convective heat to the canyon heat balance. So again, to consider the heat exchange from the roof to the outdoor environment in the two different scenarios, we modify again the original code. In the scenario A, which is the most common, the most frequent, the overall convective heat from the roof that entails both the normal convective heat and the ventilation in the air cavity is added directly to the energy balance in the boundary layer. In scenario B, which is less frequent but still possible, the overall heat from the roof is added to the energy balance in the canopy layer. Considering this approach to model the interaction of VPR with the urban environment, we carried out some preliminary numerical results, simulations to test the model and compare the results of 3 different roof typologies, which are metal roof, cool roofs, and VPR. In the next slide, the preliminary results are reported in terms of indoor and outdoor heat gains. The considered roof typologies are characterized by the same thermal transmittance but different optical properties. For the cool roof, a typical aged albedo value used in literature is considered. Future simulation clearly will consider other roof features and solutions, also considering the different thermal transmittance value and optical properties. The simulations are carried out considering a common urban scenario corresponding to a typical city center, in this case corresponding to the city center of Reggio Emilia in Italy. All the buildings are considering to have the same roof typology and to be cooled during the whole day. Let's see the first results. This is the last slide. Regarding the indoor heat gains from roof, the main difference between the different roof typologies lies in the different heat flux entering from the roof. The results obtained in the scenario A, where the convective heat from the roof is released in the UBL, show a reduction of about 35-36, going from the metal roof, which as expected is the worst performing solution, to the cool roof and the VPR solution. Similar results have been obtained from the scenario B, where the convective heat from the roof is released in the UCL, and where a reduction of about 36-37% is obtained. Thus, in these terms, the performance of cool roof and VPR are quite comparable. However, moreover, if we look to the outdoor heat waste due to air conditioning, both the cool roof and VPR solutions produce a heat released by the HVAC system in summer lower than the metallic roof, with a difference between 6 and 8% in both scenarios. It should be noted that these differences are referred to the entire building and not to the attic floor only. Moreover, due to the passive action of the cool roof and the VPR in reducing indoor overheating, a lower energy consumption and then costs are obtained in these cases if compared with the metallic roof solution. As I already said, this was the last slide. That's all from the action D1.1. As I already said, these are just preliminary results, so we will deep our results in the next month, and especially regarding the results in terms of air temperature. I am available for question if there are some. Thank you very much.
Thank you very much, Gianluca, for telling us about the development of a software to be able to model the interaction between clay, ventilated and permeable roofs and the urban environment, and then to assess their impact at urban scale. It is remarkable the comparison of the horizontal-based roof, PPR, with different roofing solutions, such as the cool roof and the metal roof. Well, once the presentation are over, we open the debate. The speakers are at your disposal to answer your questions and provide further information on the topics discussed. First of all, we will see the questions you have left us in the chat. If you prefer to speak into the microphone, just click on the raise hand icon and we will activate your microphone so that you can ask your questions. Let's see the chat. Well, there are no questions. Elena Gracia, maybe you?
I don't have any questions. Just thank you to the speakers.
Elena, if I may?
Yes. Yes, please.
It's not a question for myself, of course, just a comment, because I know that the presentation, because we had a lot of technical details, so maybe people had to think of. But just to say that we are on the social, we have a website, and we have also a newsletter. So if the audience want to be updated on the activity, And if some question will come later, as usual, I mean, it happens to me anytime, please, they can contact us and also write on the website. So they will be updated on any action and any other conferences and webinars that we are organizing.
Thank you, Giuliana.
Thank you very much, Giuliana, Elisa, and Gianluca. It seems that there are questions. So today's webinar, we hope you have found interesting and useful, is over. This was our last webinar until after the summer. We will come back with new and interesting topics in September. We encourage you to follow us on our social networks, where we will keep you updated on all our activities. You can also subscribe to our digital newsletter, and we invite you to visit our blog on the Hispalyt website, where we regularly publish current articles on ceramic products, energy efficiency, industrialized construction, innovation, and sustainability. Finally, when you close the webinar, a survey will appear on your screen about today's event. We will be very grateful if you could complete it, because it is very important for us to know your opinion in order to plan future events. Thank you very much to all of you for your interest and participation, and see you after the summer. Happy holidays.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.